I'm going to look at problem 7.15. And this problem, we're looking for the gauge pressure at the bottom of a tank with three different liquids in it, and they're immiscible, so they're not going to mix. So what we need to do is determine what the pressure is here. Okay, so we'll take a look at that. And the information that's given, of course, is the height of each of the liquids and their specific gravity. Okay, so the specific gravity is just a ratio. Okay, it's a ratio between the density and the density of water at 4 degrees C. Okay, so I'm looking for the gauge pressure. Here's the information that's given. Specific gravity of the first liquid. The second liquid, I identified them as 1, 2, and 3. And here are the heights, 12, 20, and 15 centimeters for each of the liquids. And I just converted those over to meters directly. One other piece of information, we can get from a table, you can get the density of water at 4 degrees C, and the typical value is 9,810 newtons per meter cubed. Okay. All right. So we have some governing equations associated with it. We have our general equation for change in pressure, which is just density times gravity times height of the fluid. Okay. And we also have here specific gravity, which is density of the particular fluid or liquid, in this case, that we're looking at. And that's divided by the density of water, 4 degrees C. So it's just strictly a ratio. Okay. So solution is we're looking for the total pressure, or, the pressure at the bottom, I defined it as delta PT. So it's going to be whatever pressure due to the liquid, what I identified as 1, delta P of liquid of 2, and the delta P due to the third liquid. Okay. So from that point, I just substituted in this is for delta P, so I just use the delta P equation. The density of liquid 1 times gravity times its height, density of liquid 2 times gravity times its height, and the density of liquid 3 times gravity times its height. Okay. Then I rewrote it, so I used this idea of that, the density is equal to specific gravity times the density of water. And the reason I did that, of course, is because they didn't give us the density of each of the liquids directly. They used it as in terms of a specific gravity, okay, with relation to water. So I just used this equation, rearranged it, and I pulled out, since each of them are multiplied times the density of water 4 degrees, I just pulled that out of the equation, and then multiplied specific gravity times the height, specific gravity 2 times its height, specific gravity 3 times its height. And then I can come up with, and I substitute in for the numbers for each of them, and then come up with the delta PT, or the pressure at the bottom of the tank, is going to be equal to 5,037 newtons per meter cubed. And that's pretty much it. So the thing to recognize is that, you're using this equation, but now you have to think about like the change in pressure relative to a certain position, right? Or relative to whatever pressure is being put on top of it, right? So if you think about it, the liquid on the top, in the highest part of the tank, is whatever delta P is up here, which is just since it's gauge pressure. In this case, we would just have it as whatever the atmospheric pressure is here, and then relative to this point down to here, we have this much delta, a change in pressure due to this, right? And then when you go down another layer, you'd have to add the delta pressure due to this liquid added to whatever it is for this liquid, right? When you get down to this point, and then when you go all the way down, of course, you're going to have the pressure from this, the pressure from this, and the pressure from this liquid pressing down on this object, or whatever it is, or whatever the gauge that would be at the bottom here, okay? So that's where we come up with the 3. And that's basically it for the solution of this problem.